Welcome again to a new and exclusive video about the blast load analysis in SAP 2000. See, the blast load analysis or the impact load analysis is done generally near the military areas where we are going to construct some buildings, and there are chances if something is going to get explode nearby it, or by some terror attack, or by something like you can say impact load, the building is going to get a lot of force in a very short duration of time. That particular thing is going to get analyzed in this particular video. Now what we are going to do, we are going to first learn the basics of the impact load analysis, and then we are going to see how we can import those settings in SAP 2000s. Okay, so this video is going to be a bit of a lecture and a bit of demonstration through SAP 2000 also. So let's understand it one by one. Okay, first, we need to understand what is blast loading. So it's a phenomena of a rapid and abrupt release of energy due to explosion that we know. The nearer you are to the explosion center, the more you are going to get affected through its, you can say, impulse energy. Okay, and the further you are away from that particular point, the lesser you are going to get affected. So a bomb explosion within or immediately nearby a building can cause catastrophic damages. What kind of damages? Like collapsing of walls, blowing out of the windows, and hence it is dangerous. So the blast effects are represented by a wave of a very high intensity. These are kind of waves which transfer from the center point to the outwards. Okay, now it's obvious that as that particular wave propagates, it decreases in strength and speed. It is same as like you throw water into a sea or an ocean or a pond. What it does, whenever you throw a stone, it starts spreading in the form of waves. The waves get less disturbed the farther you went away from the center of that particular point. Okay, so in the same thing, this impact load analysis work. Okay, so as the wave propagates, it decreases in strength and speed. Okay, so subjected to the blast load dependent on the selected distance. Now this scale distance is very much important. How much distance you are considering, that is very much important. Like how farther you are away from that particular center point, so that is there. Generally we use TNT as an, you can say, equivalent of that particular explosive. We, whatever the explosive we are taking in consideration, we take it as an equivalent of TNT, because there are formulas and the charts related to the TNT, so it makes our calculation much more easier to take all the impact loads into the equivalent of TNT. Let's move ahead. So this was the basic, you can say, about the blast load. Now there are some key findings that hasn't already been done in the blast load analysis or the impact load analysis. And what are those? Let's consider them one by one. The conventional reinforcement provides sufficient ductility for elements exposed to the distance explosion, and additional reinforcement is required for the close explosion. Now what they are saying, they are saying the conventional reinforcement that we are doing, it is good if the explosion is far away or it's a bit distant, but if it is close, then the additional reinforcement is required. These all findings are done from the various research papers. Okay, so second point, it is difficult to numerically predict the exact blast induced pressure field and highly non-linear response due to the modeling limitation and uncertainty associated with the blast load. It's obvious that the impact load can happen anywhere. It can be at the bottom story, it can be the mid story, it can be at the top. So what that will happen, that will induce the non-linear response, and the softwares can't handle this particular thing. What we can do in software, that we can run separate analysis by changing the height of, you can say, that particular blast load. By we can do first analysis at base, then at the mid and the top, and then we can do all the critical analysis. The third point, variation of displacement along the height of the building is non-uniform and it is different from earthquake and wind load. As we know, the earthquake loads, if we are going to do the static analysis, the earthquake is going to be like distributed linearly from bottom to the top. So that makes it totally different from this blast load analysis. Building does not behave as a cantilever structure under blast load. That's the very major thing. If the blast is going to happen, if the impact is going to happen at the midpoint, then the building is going to totally behave in a different way. It is not going to be like a cantilever way. It will be like maximum at the center and like minimum at the bottom and the top. So it will be totally different. A non-linear, or you can say not uniform response is going to be there. Structural designers should pay the special attention in the weak parts and strengthen the roof and the parapet design, since the vibration response of concrete frame is maximum at the top under blasting vibration wave. So what we can do, see, everything is kind of very not predictable in this particular impact load case. So what we can do, we can check out what are the, you can say, the parts of the building which require, you can say, more reinforcement, or the more concentration we need to pay there. So what that particular thing we can do. Similarly, regular frame structure is the most optimum model. If you are constructing near any area where this impact load or blast is going to be, you can say, there or expected, so what we can do, we can try to have a regular frame structure. Okay, that will not induce extra torsions or the movement, so that will be, you can say, perfect for us. So these were some key findings that we already know. Now let's move on to the basic load analysis graph, that is known as idealized blast pressure time graph. Okay, now let's try to see it, what this is. See, onto the y-axis we have a pressure, and onto the x-axis we have a time. What happens when an impact load happens or a blast load happens? We suddenly get a peak energy, or we suddenly get a very peak, you can say, energy impulse energy towards our structure, and then through the time it start getting decrease, and this one that is below the, you can say, the x-axis, it is the negative specific impulse, that is what that is known as, you can say, the suction. Okay, you can also study it in the wind load analysis. Whenever the wind comes after impacting, it gives a suction to the, you can say, the leeward side. Okay, so that is the same thing. Whenever the impact is going to there, it will start at the peak and it will slowly decrease. It will not slowly decrease, it will decrease very rapidly in a moment of second. Like the blast is going to be like 0.003 second or 0.05 second, is going to be very small. So the structure, the load is going to be their peak at the start point, and then it will get slow down into a very instant of time, and after that it is going to give the suction. Okay, it is going to give a negative pressure there. So P max is known as a peak over pressure, that is going to be that particular thing, it is the above atmospheric pressure. TD is the duration of positive phase, this one, and the impulse area under the curve, that is integration of PTDT, this is going to be this curve, this one, this is going to be our positive specific impulse. Generally negative specific impulse is going to be very low, so we can ignore it in our analysis. This positive impulse is going to be very big and it is going to play a vital important role, so we are going to consider this particular thing. Okay, so this graph plays an important role. Okay, now how we can make this graph for our particular case, that we'll see. Now to make that particular graph, we have, you can say, two methods. Okay, the first method is the Friedlander's equation. What this Friedlander equation does, the blast pressure decay over the time can be modeled using this particular equation, that is blast load pressure at particular time, that is T, can be calculated with this particular thing, and the formula goes like the P maximum 1 minus 1 T 1 minus T over TD and multiply by e to power minus bt over TD. Now what is the PT? Is the pressure at time T, whatever time you want to check that. For example, I want to check at 0.05 second. Now at that particular time, what the pressure is going to be, we can calculate it with this particular formula. P maximum is the peak over pressure, TD is the duration of positive phase, and B is the decay constant, which is usually 1 to 3. Now there is one thing, you can make the pressure time graph, that is pressure at the y-axis and the time at the x-axis, with the help of this particular equation. Okay, or what you can do, you can use the graphs which are already made and already are there in our codes. Okay, these are the two methods through which you can make that particular graph. Now before going on to that particular graph, we need to understand these 4 points. First is charge weight, that how much weight we are taking of TNT equivalent that is going to get impact, or that is that which is going to get blast. So TNT equivalent will be in kg, or you can say the pounds. Instant of distance, that is capital R, is the distance from explosion to the structure. Then there is peak over pressure, that is the calculated using empirical formula or chart. These are the two methods, okay, that I have discussed right now. That is how to calculate the peak over pressure with respect to time. That one we can do with the empirical formula, that is Friedlander's equation, and the second is going to be through the charts, and charts are available in UFC 334002. Okay, that I will share in the next slide. And the impulse is the total energy transferred. Okay, so now let's see what other things that are going to get happen in this particular case. The first thing that is going to get happen is the dynamic structural response. We are going to have a very large displacements in this particular impact load case. We are going to have local failures, like one of the column is going to fail but the others are going to be there. Then there are going to be rebound or vibrations, that is the generation of vacuum and the suction. potential progressive collapse is going to be there. So these all the things are going to be there in our impact load analysis or this blast load analysis. So dynamic structural response is very good. See, I'm not going to get into that much of deep, that is I'm not going to cover the potential progressive collapse and the local failures and all that. I will do in the some next video, but we can consider the basic thing, that how we can define those cases, how the structure is going to respond and like that. Okay, so let's start with an example. We are going to use this example and then we are going to analyze it in SAP2000. So example goes like this. We are going to do an analysis of a blast load example with a 5 kg equivalent of TNT, which is getting blasted at 3 meter away from our particular, that is structure. Okay, so TNT charge weight is W is 5 kg and the standoff distance capital R is 3 meter. First step that you need to do, you need to convert it to the scale distance. The formula for the scale distance goes like this, that is Z is equal to R over W to power 1 by 3. R is our that is standoff distance, W is our TNT weight, and you are going to get 1.754 and something. So this scale distance is going to get used in the charts, okay, to get the peak overpressure. How? Let's see. This is the graph. This is the graph from the code UFC334002 and it is figure number 2.15, and you can see onto the x-axis we have scale distance and onto the right hand side we have onto the vertical side we have peak overpressure. So with the help of this red line you have to consider, which is the peak overpressure. Now with the help of this, what you can do, with the help of, you can say, the Z, that is scale distance, you can find out the peak overpressure. Okay, so you can use this graph. This is idealized graph. Or the other thing that you can do, you can use this link. Okay, this is the Kingery Bullmatch blast parameter online calculator that you can use to get the values that we need to input in SAP2000. Now, how you can use this particular thing, that I will let you know. I'll hit escape. I'll go to the next slide. Where's the slide? This one. Sorry. Okay. So the link is not clickable. I'm going to copy it. Oh yes. Copy. And I'm going to, we'll need a bit of chat GPT in this particular thing. Okay, I'll let you know. So we'll go to this particular chart and you can come down here, and that is, I will provide this link in the description. So explosive type, we have a TNT, charge weight is our 5 and range is 3 meter. We'll just hit calculate blast parameter. So this is going to be the blast parameter. Okay, this blast parameter has been already shown here in this slide. I'll let you know here. Move next. So here, so step 2 is the estimated peak overpressure and duration. So two things that you can do, either you can rely on that particular graph or you can use this particular link that I have provided. So I'm using this one. Okay, so by providing this link, by inputting the value of 5 and the range 3, you are going to get all these values. The major thing that we are right now in need of is the incident pressure and the reflected pressure. That is, incident pressure is kilopascal and reflected pressure is also in kilopascal. That is 383.69 and 1571. Now the main important thing is the reflectance pressure here. The reflectance pressure is the pressure which is going to be applied onto our structure. So 1571.45 kilopascal is in need. That is 1570. We are going to take it and round up. Okay. Now let's talk about step number 3. Now what we have to do, we have to create a pressure time data. Now onto the x-axis we are going to have a pressure, and onto the y we are going to have, onto the y we are going to have a pressure, and onto the x we are going to have a time. Now we have the pressure, that is 1571, but we don't have the time right now. So it is kind of based on your experience or based on the research that what time you are going to take. Generally, the blast loads are going to be very in short duration. I am taking the time 0.005 seconds, that the blast is going to get on and off in this particular seconds. Okay, so what you can do, you can either use the Friedlander equation, or what you can use this particular equation, because this equation is quite complex. You can use this equation and ask the chat GPT to make a pressure time diagram for you. Okay, a table also can be made. So what I did, I used the chat GPT and with the following prompt, help me build a full pressure versus time table by using the Friedlander curve graph for time history input for a peak pressure of 1570 kN per meter square and a time 0.005 seconds. So what ChatGPT is going to do is going to use that particular equation, and it is going to generate a table for t is equal to 0 to 0.005 seconds for this particular seconds, and with 0.0005 second of step. That is, it is taking on 0.0005 second of steps, like steps by step. So at the starting, the whole pressure is going to be there, like that particular graph. 1500. You can see onto the left hand side, there is the graph. At the start of the, you can say, blast, whole of the pressure is going to come onto our building, that is 1500. Then it is going to get reduced like 1 2 3 4, then 991 and so on. It will come to 0 at 0.005 second. So we are going to use this particular data and we are going to generate a time history function in SAP 2000, where we are going to input all these values and then these values are going to get applied onto our structure. Okay. So after that, what we need to do, there are two main important things that we need to understand. That is the output time step size. Output time step size is what? It tells the program how often to calculate and save results. It is kind of steps. Okay, like if you want to go from one floor to the another. Okay, so you are going to use the stair. So that stair must have to be how much of steps? Like for example, it is going to have a 12 steps. So for every step, we are going to walk and we are going to calculate our results. In this particular analysis, that same thing is going to happen. We are not going to be like find the value for the t is equal to 0 and t is equal to 0.005 second. It is going to be at steps. Okay, so that steps need to be calculated. Similarly, number of output time steps must have to be known. That it tells the program how many total time steps are there. For example, I am taking 0.1 steps, 0.1 second. We want software to calculate the result at every 0.1 second, and we want 100 steps like this. So 100 multiplied by 0.1 step, that is going to be 10 seconds. So the total result will be for what? 10 seconds. Okay, so try to understand. Output time step size means for what time fraction you want the results to be checked and saved. Okay, and the number of output step means the total number of step that you need, and these both things are going to get multiplied. I'm not going to take the 0.1 second. I will take a very small value because 10 seconds is very high for this impact load. Okay, and for the real world class, what we generally use for the output time step size, we take 0.0005 second, that is 0.5 milliseconds, and number of output time step take it as 1000. So this is going to get multiplied, 1000 multiplied by 0.0005, we are going to get our 0.5 second. That I told you that it totally based on the experience and research paper, that how much seconds you are taking. Take 0.5 second, it will work for you. Okay, so now let's dive into our SAP 2000 and let's see how we can define the load cases, how we can assign these all the things and all. Okay, so this is SAP 2000. What I have did, I have made a very uniform, you can say a 2D 3D structure here. And first what I did define the section properties. I have a beam with 250 mm by 500 mm of depth. I have a column of 500 by 500 mm. I have also defined a wall here, like section property and area section. I have defined a wall here. There is a wall here. Okay, and this wall has been matched also. Okay, it has been matched to get, you can say, more refined values. Okay, now the next thing that you have to do after defining is to go into the functions, and you need to define a time history function. I have defined a blast function, and this function is going to be like you have to use user here. Okay, and then you need to define it. Now when you are going to define it, it is going to ask you the time at the left side and the value at the right side. What you have to do, you have to go to our chat GPT answer that we got, this one, and you need to put all this value like 0.00 1500, that needs to be put at this particular starting point, and then you click add. Similarly, you do it for all the other values. Okay, for 0.005, that one must have to be 1 2 3 4. Okay, so this is how you need to do. I have inserted all the values here, and this graph is going to be automatically made into the bottom side. So you can see the pressure wave will be maximum at that particular point, and then it will start decreasing and so on. Okay, so this is how you can define a time history function. Name is at a blast function. I have named is a blast underscore function. Then you can go on to define. So function has been defined. Go to load patterns and define a blast underscore load underscore pattern. Naming can be done as per your convenience. I have done like this in sentence case by using a underscore. So I have defined a blast load pattern with the type other, and I have just added it. Nothing is going to be more here. Just add it as an other load case. The third thing that you have to do is to go to load cases and define a new blast load case. Okay, I have defined this blast load case. And when you are going to do this, you need to select blast, that is time history, as the load case type here. The moment you are going to consider this thing, all the options are going to get changed. You need to consider non-linear analysis at that particular point, because the things are going to get non-linear. You can also do the analysis for, you can say, the linear analysis for the study purpose. We are try to do the model analysis here. The history is going to be transient, and then in this particular box you need to pay attention. First is load type. So load is load pattern. We are applying a load pattern. Now in which particular load name we are storing those values. So we are doing it in blast load pattern. Okay, that is the load pattern. That was the type in that was other as a type, that was used as a other as type. And the main thing is function. This function needs to be selected here. Scale factor needs to be 1 because it is in scale. If you want in negative x direction, you can put -1. Okay, time factor and all things must have to remain same. The angle you can check. I am right now doing it as 0 degree, like from the x direction. If you are going to put it as 90 direction, it is going to take the other direction. Okay, now the main thing that we have discussed earlier, that is the time step data. Number of output time step, I am taking 1000, and output time size, that is I am taking right now 0.003. You can also take 0.0005. Let's take 0.0005. Okay, and this is the model damping, that I will take it as 5%, and these are the non-linear parameters. If you are doing the non-linear analysis, you need to check these parameters. So these are the major things that you need to consider. Okay, the load pattern, the load name, and the function and all that. Okay, so what the software is going to do, it is going to use this function, that is the application of you can say the force is going to be handled through this function, and it is going to store in this particular load name, and this load name and all the things are going to store in this particular load case. Okay, so I'm going to press OK here. So we have a blast load case, we have a DAD case. DAD and models are by defined is there. Okay, I'm going to press OK. Now there are load combinations also for impact load analysis. What we do in that particular case, whenever we are going to use a blast load and impact load, we are going to use dead load plus the blast load. We are not going to include the earthquake load or the wind load with this particular case, because that is going to make our building very much critical. So in every code you can see we are going to use dead load plus blast load. A bit of fraction of live load is also used in some of the codes, but we can ignore that particular particular thing that at this particular time. Okay, so I'm going to add a combo here, that is dead load plus BL. I'm going to write as plus BL for the blast load. I'm linearly adding. So first I'm going to take a linear load, I'm going to add it, and then I'm going to take the blast load and I'm going to add it. So dead plus blast load came. Okay, okay. Okay, so the one case has been defined. So only one case we need right now. Now everything has been done and defined. You can just go to analyze and you can just click on run analysis. Okay, I'm going to run all of these things. I'm going to click run now. So what you have to do, first we have to define the function, then second you have to define the load case, and the third second case you have to define the load pattern. Third case you need to define the load case. Okay, and if you want then you can go for the combination. So this is right now the result. Let's see the results one by one. I want to see the XZ plane here. Okay, I want to see in this particular plane. So I'm going to come here and I'm going to click XZ so that I'm going to see in XZ plane. Then I'm going to hit this particular option, that is show deformed shape, so that I can see the cases. You can check the deformation for any specific, you can say, case or the combinations. I'm going to take a combination of dead load plus live load. I need the step case, that step 1, 2, 3, like I want to check for that every 0.0005 second. And scaling, you can check the diagram scaling. You need to check this scaling. Okay, if you are going to use it automatic, the deflections are going to be very low, it is not going to be visible. So for the user defined, you can go and try 1, 2, 3 like that. Okay, I'm going to apply. And onto the right hand side you can see there is a step 1 and the structure is there. If I press this next button here, we are going to see the step number 2nd and then step number 3rd and so on. So right now the things are visible, but a very you can say in a very small way. Let's zoom it. I'm going to zoom it in so that we can see the values more clearly, or we see the you can say graphics more clearly. So in this one scaling, the things are not looking good. Let's go for the t is equal to for the scaling 2, and let's try then for the step 2nd, step 10. Now there is a bit of, you can say, deflection that we can easily see. Okay, let's take it as 3. Okay, and hit apply, and then to the next. Nothing. Now the graphics is looking good. We can do the start animation thing here. Okay, we can start animation. This is going to record the animation. and it is going to tell us that how the structure is going to vibrate. See, the structure is getting vibrated like this. Still the values are not that much, the graphics are not that much, you can say, scaled up. Okay, so let's stop this particular thing and let's make it big like 5 and hit apply. I'll start animation. Now we can see it is visible right now. I'll stop this one and let's see a bit more. I'll go 20. I'll hit apply. I'll start animation. The structure is looking like this. We can also see this particular, you can say, variation in the 3D diagram also. Activate this particular 3D and we can click on start animation. You can see this animation is looking like this particular thing. If you think this thing is going very fast, you can slow it from this particular scroll bar. So this pressure is going to be like this. Okay, see, we'll see it one by one. Okay, so that we can understand how the suction is going to go, happen and like that. So that is step number 3. We are going to go on to the step number 1. Okay, this is step number 1. Okay, a little bit of, you can say, impact has been happened on the front wall. Second, it is bending inwards because of that impact. This is third. You can see now that these side walls are going to get deformed. See, they are getting outward. This one is getting inward and these were are getting outward. Similarly, into the third step also, into the fourth step also. Okay, seventh, eighth. See, this front wall has gone for just 0.0004 second. This much of impact has been done on our wall. Okay, now see, these walls are bulging out. Next, next. You can easily see. I can also start the animation, but in the animation is going very fast, so that will create the problem. See, these walls has been bulged out very well. The back wall will now get deflected. Okay, see, the back wall is now getting distributed also. The front wall is now getting inwards, that is the suction is going to be done at the bottom side, at the previous side. See, the whole geometry of the back wall has been disturbed and this wall has been completely bulged out. The front wall is now redirecting at this particular point. That is the main impact has been done. Now the impact is getting reduced. The suction part has been there in this particular position. I'll do the next. See, the whole of the geometry has been disturbed. This disturbance has been seen because I have scaled up the diagram. Okay, in real this is not going to be the like particular this thing. Okay, now see, the back wall is, because of the suction, it is getting inwards. You can go at any point and you can just hover your cursor there and it is going to give you the u1, u2, u3 values. Like in u1 direction, that particular point is moved how much in mm, and then u2 that is y, and u3 that is z direction. Okay, so you can also check the values like this. Okay, this thing is going like this. So through this particular step you can check the variation of our, you can say, the points, the frames and the shells also. The next thing that I want to show you, that you can go into display and you can see the plot functions. Now in plot functions, what you can do, you can display the graph of a particular node. Okay, see, for example, if I go here and I click show undeformed shape, and there is a point here at this particular position, I'll right click on this particular point. This point is 2. This node is numbered as 2. I want to see how much this 2 number node is going to get deflect in this particular time history function or this blast load function. So what I can do, I can go into display and then click show plot function, and then I'll take this one, remove. I'll click define plot function. Make sure the blast load case is selected at the top. I'm going to select the joint displacement force function here, and I'm going to click add plot function. And what joint I want to use, joint ID must have to be 2, and what I want to check, I want to check the displacement here. Okay, I'll click OK and then click OK. So joint 2 has been added here. I'll add it onto the vertical function, and here you can set the time range from 0 to 0.5 or whatever you want, and you can click on display. It will display the, you can say, the displacement of that particular node as per the time history function. You can see at the start this is going peak at around 0.009 mm, that like you can say I have a cursor here, it is going like this, then it is going very low after some second, and then it is going down 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 and like that. It's obvious that impact is going to come, all of the force is going to get applied, so the highest deflection that we are going to get is at the starting of the point. So this is how the graph. So similarly you can check another joint also, like for example I go here and I'll check this one. Okay, this is joint number 6. So same, I am going to click the display, then show plot functions. I'll remove this one, I'll define I will define a plot function. I'll go to the joint displacement forces, add plot, and what is my joint ID 6 number. I want to see the displacement. I'll press OK. I'll press OK, and I'll take this one into this particular side and I'll hit display. So this is the plot function for what? Joint number 6. It is going a bit less, like 0.004 something, 0.004 it is going, and then it is decreasing. It acts as an kind of, you can say, time history function, so that you can say verify our you can say the assumptions. Okay, you can also change the colors here. If you are not able to see it in like green, you can change the red color. You can take the screenshot of this particular thing, print graphics, print tables, and you can take this value into your study. Okay, so in this particular video, what I showed with the help of, you can see the codes UFC, and with the help of ChatGPT, what you can do, you can define a time history function which will help you to simulate impact load on a particular structure. Okay, now the second thing that I want to show you is that you can also change the directions. For the go into define function, in function, and where we have the time history function, show function. In this particular thing, we have all these functions applying in the x direction. If you want it in the minus x direction, what you can do, you can go into define, and then you can go on to the load cases, and this particular our load case, what you can do, you can change the scale factor as -1. It will be in negative x direction. If you click show advanced load parameter, there is an angle option here. You can use it 90° for the y direction, and if you do 90° angle and scale factor as -1, it will be in minus y direction. Okay, so you can change directions also. So I have not included the progressive collapse and all those things here. If you want a video on progressive collapse, I can make a separate video on this particular topic. So this particular video, that's all. Try it by yourself. If you got any issue, then please do let me know in the comments. Thank you. Bye bye. Take care.